Right, good morning, Matrix. This morning we're going to look at the questions that you've sent us, and we love the questions and all the comments. Keep sending them, but some of you will have to be patient. I've already received a lot of questions about work, energy, and power, and that is only scheduled for next week. Right, so today we are going to look at all the questions or some of the questions that sent in about chemical equilibrium. And the very first one I want to look at is a question sent in by Lerato. Now, this is maybe not a perfect quality photo, but it is good enough for us to look at, and it's a nice question to look at. So let's look at this one. They tell you that a reversible gaseous reaction is allowed to reach equilibrium in a closed container at different temperatures and pressures. And the graph below shows the percentage yield for this reaction at 30 kilopascals as the temperature increased. Right. Now, first of all, let's talk about percentage yield. This is something that you've done in your mole calculations, percentage yield. And when we get to mole calculations in our fourth cycle, we will look at that, but today we need that. So what is percentage yield? Now, first off, remember, when you've got an equation, the things on the left-hand side we will call reactants, and that gives you products, right? So percentage yield is how much product do you get from what you could have got. If you've got a test and you have 8 out of 15 and you want your percentage, you said that is the possible or that is the actual marks that you got out of a possible 15 and then times 100. So percentage is always the actual divided by the possible, right? Actual divided by possible. So here it will be actual yield divided by possible yield and times 100. Now remember, if it is a single arrow, it means that everything that can react will react, and you get all the limiting agent will react, and that will determine your product. But the moment you have a reversible reaction, remember, the moment that you start, you've made the first product, it will start decomposing as well, right? Doing the reverse reaction. So never ever will everything be in the product state. So that's why this is very important now, because it's actual yield. How much is really in the product state about how much could have been in the product state if it was a single arrow, if it was not a reversible reaction. Right, so we are looking at that. How much formed of what could have formed. Now that is percentage yield. And if you look at this one, you have to look at the graph. And what does the graph tell you? Now, guys, this is not a straight line, right? Can you see that? It's not a straight line. If it was a straight line, then my percentage yield and my temperature was directly proportional. Then we would have said, if I've got a certain temperature, I've got a certain percentage, and if I double the temperature, I will have doubled the percentage. That would have been directly proportional. But this is not a straight line, so it's not directly proportional, right? The only thing that we can tell from the graph is when the temperature increases. Now, if you look at this one, if you've got a T like this, you've got a percentage over there. If the temperature increases, right, you've got a new bigger temperature, then you will have a higher yield, right? So that will be a bit bigger pressure. It's just not in the same ratio as directly proportional. But we know a bigger temperature will have a bigger percentage yield. And now for the questions. Use the information in the graph above to answer the following questions. Now, we're not going to look at stating the principle. You are going to learn that on your own, but we are going to look at the second one. The heat of the reaction, delta H, for the forward reaction is positive. Right. Now, sometimes they ask us if it's positive or negative. Here, they tell us it's positive, and then they ask us to explain why it is positive. Right. So what did we learn from the graph? We learned that when the temperature increases, the percentage yield also increased. Right. Now let's start. It's two things talking about the same thing. So first off, what does it tell us if the temperature increase? What do we know about the temperature increase? What does Le Chatelier tell you about an increase in temperature? If the temperature increases, then the system will react to oppose that disturbance, and it will decrease the temperature by using energy, right? And what type of reaction use energy? That will be the endothermic. So that tells me that the endothermic reaction will be favored, right? But when I look at this is the result of whatever happened. Whatever happened produced a better yield, right? So it made more product. And if it made more product, which is on the right-hand side, it tells me that forward was favored, right? Only if forward was favored will I end up with more things in my product state, therefore a bigger percentage yield. And those two things are talking about the same happening. So that means that my forward is actually endothermic, right? And that tells me delta H is positive, right? So if they ask that for 3 marks, it will definitely be because you tell them that an increase in temperature is always, according to Le Chatelier, going to favor the endothermic one, right? The fact that we have an increase in yield tells me that forward was favored, and that's why I can say forward is endothermic, which means it's positive, but that they already gave us, that's why it's not a mark. Right, so we're moving on from Lorata's question, and now I've received quite a few queries or quite a few people asking for us to look at the 2019 exam paper, last year's final exam paper. It is available on the internet, right, at the government site, but the memo is not yet there. So let's just look at this. Now, they tell you that initially 60.8 grams of pure carbon dioxide is reacted with carbon, right? You've got the carbon, you've got the carbon dioxide in a sealed container. Yes, we need that, otherwise we can't get equilibrium, and they give us the volume of the container, right? Now they tell us the reaction reaches equilibrium at a temperature T according to this balanced equation. First one's a definition, we're going to skip that. Let's look at the second one. At equilibrium, it is found that the concentration of the carbon dioxide is 0.054 moles per cubic decimeter. And now they ask us to calculate the Kc value. Now, guys, if you are looking at this, they are talking about Kc. And for Kc, the Kc equation for that one would have been CO to the second divided by CO2, right? And remember, the solid does not come in, right? It's got a concentration of 1, so we are going to ignore that. So it is not in there. We are going to look at that. But what we need here is the concentrations at equilibrium. And they give us one concentration at equilibrium, but then they also give us things at the start. And remember, if you've got things at the start and things at equilibrium, you have to be careful what you're working with. And a nice way to do that was that Kc blocks, right? So that was the moles initially, then the moles that reacted, and then the moles that you had left over at equilibrium, and then the concentration, so that we have the concentrations to put in there. Right, now let's start off. They tell us that initially 60.8 grams of pure carbon dioxide react. So they don't give us moles initially, they give us mass. But this is easy. Converting mass to moles, I'm working with 60.8 grams. Big M, molar mass, go to the periodic table, and we're looking at the molar mass for CH2. That would be 12 for the carbon and 2 times 16 for the oxygen, and I end up with 44 grams per mole, right? Okay, and if you divide by 44 there, you end up with 1,382 moles, and that is now of CH2, and that is at the beginning. So I've got 1,382 moles, right? Now, they're not telling me how much carbon. I definitely need carbon, otherwise the reaction can't happen. But then they go on and they tell me once we've reached equilibrium, then the carbon dioxide, and always remember to read very careful. Don't put it in the wrong column, right? Carbon dioxide, and they don't give me a mole, they give me concentration. So that's 0,054, and that is in moles per cube decimeter. Right, now the other thing that you had to read between the lines is if you've got, initially they only put CO2 and carbon in a sealed container. So they said nothing about CO, and I can take it for granted that there's nothing to start with. Right, now in this column we've got more than one. So this is the way to start, to say I've got the CO2 concentration at equilibrium. Let's just go back and see how many moles. Right, so how do I go back? Now, when I've got moles, I have to divide by volume to got concentration. So going back, I will multiply by 3. Right. Now, if you multiply that by 3 times 0,162. Right, what does that help? Well, I started out with that, and I ended up with that amount. So if I subtract, then I will know how much reacted. So I take that and I subtract that, and I end up with 1,22 moles. Right, now I would like to put a small minus there. You don't have to. Most teachers don't, but this is to remind me that this is being used. Right, now if you look at the equation, everything on the left-hand side, if I'm using that, I will definitely be using that as well, and this will be produced. Right. Now, if I have that, remember, this reaction will react according to the equation. Right. It reacts according to the equation. So now when it reacts, it will be in the ratio 1 to 1 to 2. It was not true for what we put in. Remember, the guy who put it in, he decided how many to put in, right? But they reacted according to the equation, right? So if you have 1.22 of that used, you need twice that, 2,44 of that will be produced. And if I produce that, it means I end up with that. And then to get to concentration, I will take my moles and I will divide by 3 because that is the volume, and I end up with 0,813. Right, and then it's just a question of putting it in there. So now I've got 0,813, and remember to square, divided by 0,054, and if you do that, you end up with 12,24. Right. So this has answered the first question. Now let's look at the second one, the next one. Now they ask us, what is the minimum, very important, what is the minimum mass of carbon that must be present in the container to obtain this equilibrium? Right, remember, if you use carbon dioxide, obviously you have to use carbon. Now, if they tell me they are looking for the minimum mass, it means I don't need anything left over at equilibrium. Remember, solid does not even have a concentration, so that is definitely not something that I have to fill in, but I don't need anything left over. I just want the minimum, so all of it can be used. Now, what do I know? They're in the ratio 1 to 1. So if 1,22 of the CO2 is used, it also means I have used 1,22. And if nothing can need to be left over, then it means I started off with 1,22 moles. Right. So for B, or 6.2.2, when they're asking what is the minimum mass, now the moles that I need is 1,22. To convert to mass quickly, moles 1,22, and mass, molar mass for carbon 12, and I end up with a mass of 14,64 grams. Right, 14,64 grams. Right, so that is the minimum mass of carbon that I need for the others to be able to reach that equilibrium. Right, moving on. How will each of the following changes affect the amount of carbon monoxide at equilibrium? Now, careful, where's the carbon monoxide? On that side, right. Now, first thing, They're adding more carbon. What do I know about carbon? Well, the carbon is a solid, right? And if you remember correctly, we said that the carbon, if it's a solid will not affect equilibrium. So here the answer was just, it remains the same, right? It remains the same. Because the carbon is a solid, and a solid does not affect my equilibrium. Right, next I'm moving on to pressure. Right, if the pressure is increased by reducing the volume of the container at constant temperature, use Le Chatelier's principle to explain. Right. So the first mark is for what's happening to CO, but that's the last thing that I'm going to be able to give them. Right, so let's start off. They are telling me they are increasing the pressure, right? Remember Boyle's law, volume and pressure inversely proportional, right? So if I decrease the volume, reduce the volume, the pressure will increase. So that is the disturbance. And then what does Le Chatelier tell you? Le Chatelier tells you that the system will react to oppose this, right? So what my system will do is my system will react to decrease the pressure. So how can it decrease the pressure? It can make things that don't press that hard. So the carbon doesn't press. A solid is something that's lying at the bottom of that container, right? Gas are the things that are pressing. So if you look at this equation, you will find on the left-hand side, there are only 1 mole of gas. And on the right-hand side, there is 2 moles of gas, right? So if the system wants to exert less pressure, it needs to make less moles of gas, right? Because gas are the things pressing against the container. So you need less moles of gas, and in this instance, it will mean the reverse reaction is favored. Right, but we still haven't answered the question. The question was what's happening to the amount of CO? And if the reverse reaction is, the amount of CO will decrease. Right, so that is actually the first mark, decrease. And remember with things like that, there's negative marking. If you don't have that right, then they don't mark your explanation. You can't explain a wrong answer correctly, right? So you need to have that before they're going to look at that question. Right, moving on. Now they tell us the table below shows the percentage of CO2 and CO in the container at different temperatures. Right, at that temperature, there's 6.23% of CO2 and 9.377% is carbon monoxide. And now they ask, is the reaction exo or endothermic, and explain by referring to the graph. So let's start off on this side. If I go from there to there, it means I go to a higher temperature, right? So when the temperature increases, what's happening to the percentage carbon? The carbon monoxide, it's also increasing. So the percentage CO is increasing. And what is CO? CO is a product, which means I've got more product, right? So if the temperature increase, I will have more product, and that can only be the result of the fact that the forward reaction was favored, right? And that immediately tells me things that I can use, right? So I'm going to say when the temperature increases, the percentage carbon monoxide increases. Now, what do I know about an increase in temperature? Well, according to Le Chatelier, the system will react to decrease the temperature by using the energy. So that means it will favor the endothermic, right? An increase in temperature will always favor the endothermic reaction, right? The fact that I have more product can only be the result of the fact that forward was favored. And from those two, I can see that forward is endothermic, right? Forward is endothermic. so that was the answer to the first question. Right, next one. Use the information in the table to determine the temperature T. Right, so what can we get from this? Now, what do I already know about T? I already know at T, that is when I did my my reaction up there, right? That was at a temperature T. So I already have, when I have equilibrium, I already know how many moles of CO2 and CO were in the container at equilibrium. So what I can do is I can say, okay, let's work out what is the percentage of CO2 and what is the percentage of CO when we have our equilibrium at time T. Right, so we already know at equilibrium we've got in our container 2,44 and 0,162 moles of CO2 and CO and nothing of the carbon. Right, so now we can say the percentage CO at that time at equilibrium is the 2,44 moles of CO that we've got divided by all the moles in that container, 0 and 0,162 and 2,44. So the moles, that's only CO divided by all the moles times 100. And that gives you 93.77%. And then if you go back to your table, you will see if the CO percentage is 93.77, that tells us we are at a temperature that is 827, and just check the unit degrees Celsius. Now, I would have liked them to tell you that it is percentages and it is percentage mole. Right, because they could also have had percentage of mass. Right, then you would have converted the moles to mass before getting the percentage. Right, but here they were working with the percentage moles of CO2 and CO in the container. Right, so that was last year, the final exam. Next on, there were a few guys who asked me to look at the question that I asked you on your worksheets. Now, they said ammonia is introduced into a flask, which is then sealed and allowed. So they only put ammonia in, right? So at the start, there can only be a forward reaction, right? Which is then sealed and allowed to reach dynamic chemical equilibrium at a certain temperature. The balanced equation for the reaction is this, right? Now the graph below shows the changes in the rates of the forward and the reverse reaction with time, and the dotted line represents forward. Does that make sense? Yes, it makes sense, because they only introduced ammonia, so we only had the forward reaction had a rate to start with. No N2 and H2 at the start, so we had a zero rate, right? And then they got equilibrium. First question, write down the reaction that is represented by the solid line. Now this is the easy one. Hey, they already told us the dotted line is forward, so we are talking about reverse. Right, now so what do I have to write, and what can I do wrong here? So you have to say N2 plus 3H2 gas is going to give you 2NH3 gas. Now these two can switch around because that's what I put in. They are reactants, right? But the two sides can't switch around, and you definitely need only a single line, right? Because that solid line only refers to the reverse reaction, right? The dotted one is the forward reaction. So make sure that you've got the single line, otherwise you won't be able to get that mark. Next up, they asked, explain why the rate of the reverse reaction increased as shown on the graph during that first 60 seconds. So we're only looking at that part, and they are asking us, why is the rate of the reverse increasing, getting higher? Now, to answer this, I have to say, when I started out, the N2 and the H2 were zero concentrations, right? They didn't put any N2 and H2 into that container. So we started off with a concentration of 0, and then as the reaction occurred, the N2 and the H2 concentrations increased, Right, because it was produced. Right, so the N2 and the H2 was produced, and therefore, if you've got more of them, you've got more collisions that can happen, and that means the rate of the reverse reaction is increased. Right, so they're asking why is it increasing, and you have to explain. It is because the forward reaction that is happening faster is increasing the N2 and the H2. And therefore the rate of the reverse reaction will increase. Right. Next, we're being asked at time 120. Right, so I'm looking at 120. Now, when we look at this graph, let's just remind ourselves what we did in video 3. In video 3, we said if we are adding or removing something, you just influence the rate of one reaction, right? If you add something, there's a reaction that's going fast, and who's going faster? The one that's using the things that I add, right? I've added A2, that made the forward reaction faster, but at that moment the reverse reaction was not influenced, right? When I removed something, the rate of one of the reactions was negatively influenced, right? If I remove B, there's not enough particles, not as much particles to do the forward reaction, and then the forward rate dropped. So adding or removing only influenced the rate of one reaction, and then they sort of sorted it all out, right? But when you got to a volume or a temperature change, now for the first time, both of them are going up or down, right? Both of them are going up and down. It's just that one of them are influenced more than the other, right? Both are going down. So if it's volume and temperature, remember both will be influenced. Right, so over here, you can immediately see both of them are influenced over there. They are both going up. It's just that one is going up higher. So that must either be a volume or a temperature. And there's the same thing, right? So it's either volume or temperature. And now they tell us that it is a volume change, right? And the first thing they ask us, is the volume increased or decreased? Now, this you can answer by thinking about concentration, or you can answer by thinking about power, about pressure. What do we know? Pressure is inversely proportional to volume. And when we look at this graph, the rates are going up, right? If the rates are going up, it's because the pressure is bigger, and the pressure can only be bigger when the volume is smaller. So this is volume is decreased. Right, the volume is decreased. And if you have to explain that, it means the pressure is increased and therefore the rates increase. So the fact that it's going up and not going down, right? If the volume was increased, the pressure would have decreased and everything would have been going down, right? But it's going up. The rates are going up, and the rates are going up because the pressure is up, which tells me the volume was going down. Next, the graph shows at time 20 that the rate of both reactions increases immediately. Why is this so? Right? Both reactions increases immediately. Why do they both increase? Well, when the pressure increases, remember, they are all in the same container. So you can't only increase the pressure of those or only increase the pressure of those. When you increase the pressure, you increase the pressure on this side, which means the forward reaction is faster, and you increase the pressure on this side, so the reverse is also faster. Right, so all of them are in the same container, and therefore the pressure increase for the reactants and the products, right? For the reactants and the products. And therefore the rate increase for forward and reverse. Right, so both product and reactants have an increase in pressure. And if you wanted to, you could have talked about concentration as well. Remember, concentration is also inversely proportional to volume, right? So an increase, a decrease in volume would also have increased the concentrations, right? So then we would also have had a faster reaction. Right, which reaction is favored between 120 and 150? What does favored mean? Favored means it's faster than the other one. So if you look at here, between 120 and 150, who's got the higher rate? Remember, rate increases upwards. So who's got the higher rate? The solid line, and the solid line was our reverse reaction. So you just have to look at the graph to see it's got a higher rate, right? Now explain why it's got a higher rate by applying Le Chatelier's principle. Right, let's do that. So the volume was decreased, and immediately what is my disturbance? The fact that the pressure is increased. Right, if the volume is decreased, pressure is increased. And then, according to Le Chatelier, the system, Le Chatelier, right, what's happening is the system will react to decrease the pressure. Right. And how can it decrease the pressure? Who's exerting pressure? Remember, only gas can exert pressure, right? So the way to decrease pressure will be to make less moles of gas, And if I go back to my equation, on this side, I've got 2 moles of gas. And on that side, I've got 4 moles of gas. Right, so if I want to make less moles of gas, I have to favor the reverse reaction. Right, so I have to favor the reverse reaction. And that was what I had to explain. I had to explain why the reverse reaction is favored. And then they ask me, how does the Kc value at 150 compare with the Kc value over there? Now remember, Kc can only change if it's a temperature change. So it will be the same, right? It will not change because it's not a temperature change. Kc can only change with temperature. Right, moving on to 4.4, now we're looking at 180, and now they're telling us this is a temperature change, right? Now remember, if I increase the temperature, then the rates are going faster, so it will be going up. If I decrease the temperature, then the rates are going down. It's just a question of who's going up and down the most, right? So remember, they're both going up or both going down, but then you have to check which one is favored, which one will be lying at a higher value. Right, so is the temperature over here increased or decreased? Now, the fact that the rates are decreasing is telling me that the temperature is decreased. Right, how do I explain that? I explain that by saying that the rates decreases. And the rates will only decrease if the temperature decreased, right? So one is for decreased and the other one is the reason. Now they ask, is the forward reaction endo or exothermic, and explain by applying Le Chatelier's principle. Right, now what can we see from the graph here? We know it's a temperature change, and since the rates are going down, we know the temperature decreased, right? But from the graph, we can also see which one is favored. The dotted line has got a higher rate, right? So my graph is also telling me that the forward was favored. Right, because I've got my dotted line higher up. It's got a bigger rate, favored. Now, what does Le Chatelier tell me about any decrease in temperature? According to Le Chatelier, any decrease in temperature will make the system react to produce energy in order to increase the temperature, which tells me exothermic must be favored. Right. Now, a decrease in temperature will always favor exothermic, but my graph showed me that forward was favored. So immediately I can say that means forward is exothermic. Right. So here the first mark will definitely be for you to say it's exothermic, and then we have to explain any decrease in temperature always favor the exothermic reaction according to Le Chatelier. And from the graph, I can read the fact that the forward reaction was favored. Okay, moving on. Next one. How does the value of Kc at 150 compare with 180? Oh, I think this is a typing error, right? We've actually copy and paste there. Right, so I'm not looking at 150. I'm looking at around 200 and at 50. Right, at 200 and at 150. Right, 200 over there, 150 over there. What do we have between there and there? Now, if I want to talk about the Kc, it's definitely going to change because I've got a temperature change, right? And if I go to my graph, what is my graph telling? Now, one thing that I know is that the dotted line is lying at the top. So my graph is telling me that the forward reaction was favored. And what does the forward reaction do? It makes my products more, and at the same time it makes my reactants less. Right, so my product is more and my reactants is less. And what do we know about Kc? Kc is my products divided by my reactants. Now, an increase in products would already have caused my Kc to increase, but we also have a decrease in reactants that will also make my Kc value increase. Right, so the Kc value, how does the value compare? It will definitely be higher. Right, it will be higher at 200 than at 150. Right, 4.5, name a change in reaction conditions that can explain the graph at 240. 240? Well, the one thing that I know that can do that will be adding a catalyst. Right, a catalyst will make both reactions equally faster, right? So they will be equally faster. Right, so this is just a catalyst that is added, and then they ask me, how does the concentration of a H2 change 230 to 50? So that's before and after the catalyst, right? And the concentration doesn't, it is the same, right? So both rates are faster, both rates increase, but they increased equally. Right, so they both increase, but they increase with equal amounts. So the forward is still happening at the same rate, right? And therefore the concentrations don't change. For every one that is removed, one is made, right? So before the catalyst, it was maybe 2 was removed and 2 was returned. Now it's maybe 10 is removed and 10 is returned, but it means the amount of NH3 is staying constant, the concentration is staying constant. Right, guys, I think this was a nice questions. I want you to send a lot more on work, energy, and power for next week. And remember, anything that you need, you send the questions to the junior Tukkies, and either in this class or during the week, they will send you an answer. Right. Enjoy the work, and the next